The competency in this lesson is derive inductively the relations among chords, arcs, central angles, and inscribed angles. This is part 3. Specifically, we will be talking about tangents to circles. A tangent to a circle is a line coplanar to the circle that intersects the circle at exactly one point. This point is called the point of tangency. In our figure, line L is tangent to circle O. Point A is called the point of tangency. A common tangent is a line tangent to each of two coplanar circles. We have here two coplanar circles, circle O and circle P. So line L is a common tangent because it is tangent to both circles. Line M is also a common tangent because it is tangent to both circles. A common tangent has two cases. The first one is a common internal tangent. It is a common tangent that intersects the segment that joins the centers of the circles. So here, line L is a common internal tangent because it intersects line segment OP that connects the two centers of the circles. The second case is a common external tangent. It is a common tangent that does not intersect the segment that joins the centers of the circles. So here, line M is a common external tangent because it does not intersect the line segment OP that connects the two centers of the circles. Two coplanar circles are tangent to each other if they are tangent to the same line at the same point. Here we have two coplanar circles, circle O and circle P, and they are tangent to line L at point A. In our second figure, circles O and P are coplanar circles, and they are tangent to line M at point A. The first case is called internally tangent because one circle lies in the interior of the other except for the point of tangency. So circle P lies in the interior of circle O except for point A, which is the point of tangency. The two circles here in the second figure are externally tangent because each circle lies in the exterior of each other except for the point of tangency. Circle O is in the exterior of circle P, and circle P is also in the exterior of circle O except for point A, which is called the point of tangency. A circumscribed polygon is a polygon whose sides are tangent to a circle. The polygon is circumscribed about the circle, and the circle is inscribed in the polygon. In our figure, triangle PQR is a circumscribed triangle because all its sides PQ, QR, and RP are tangent to circle O. So we can say that triangle PQR is circumscribed about circle O, or circle O is inscribed in triangle PQR. We have three theorems in this lesson. The first one is the tangent line theorem. So it states that if a line is tangent to a circle, then it is perpendicular to the radius at its outer endpoint. Line L is tangent to circle O at point A. So this means line L is perpendicular to line segment OA. The second theorem here is the Line-Tangent Theorem. It states that if a line is perpendicular to the radius at its outer endpoint, then it is tangent to the circle. So this line L is perpendicular to line segment OA, so it follows that line L is tangent to circle O at point A. The third theorem is the Tangent-Segment Theorem. It states that if two tangent segments are drawn to a circle from an external point, so we have an external point here, point P, and we are going to draw two tangent segments. So we have line segment AP and line segment BP. So it states that the two tangent segments are congruent. So that means line segment AP is congruent to line segment BP. And also, the angles between the segments and the line joining the external point to the center of the circle are congruent. So this means that angle APO is congruent to angle BPO. Now we are going to do problems applying the theorems. Problem number 1. We have here in our figure circumscribed triangle ABC. BY equals 5, CZ equals 3, and AZ equals 8. So find the perimeter of triangle ABC. Since BY equals 5 from one of our theorems, so BX is also 5. Since CZ is 3, so that means CY is also 3. Since AZ is 8, AX is also 8. Now that means AB is 8 plus 5, which is equal to 13. Then BC equals 5 plus 3, which is equal to 8. And AC equals 8 plus 3, which is equal to 11. So the perimeter of circumscribed triangle ABC equals line segment AB, which is 13, plus line segment BC, which is equal to 8, plus line segment AC, which is equal to 11. So 13 plus 8 plus 11 equals 32. Problem number 2. Given circumscribed quadrilateral ABCD, AZ equals 4, BX equals 3, CX also equals 3, and TY equals 2. So find the perimeter of quadrilateral ABCD. Now since AZ is 4, that means AW is also 4. Since BX is 3, BW is also 3. Now since CX is 3, so this means CY is also 3. Since DY equals 2, that means DZ is also 2. So line segment AB equals 4 plus 3, which is equal to 7. Line segment BC equals 3 plus 3, which is equal to 6. Line segment CD equals 3 plus 2, which is equal to 5. Then line segment AD equals 4 plus 2, which is equal to 6. To find the perimeter of circumscribed quadrilateral ABCD, we will just add all the sides up. So that means 7 plus 6 plus 5 plus 6, which is equal to 24. Problem number 3. In our figure, line segment AB and line segment CD are tangent to circle O at point A and C respectively. AB equals 24 and OB equals 26. Find the perimeter of triangle OBC. So first, we are going to find the length of line segment OA. We have a right triangle here. So this side is 24, this side is 26. And to find line segment OA, we will use Pythagorean theorem. C squared equals A squared plus B squared. Our hypotenuse here is OB, and then we can assign OA as our side A and then AB as our side B. So we have side OB squared equals side OA squared plus side AB squared. Substituting, we have 26 squared equals side OA squared plus 24 squared. So 26 squared is 676 and 24 squared is 576. So we have 676 equals side OA squared plus 576. Subtracting 576 from both sides, we have 676 minus 576 equals 100. So we have 100 equals side OA squared. To get rid of the squared here, we are going to find the square root of both sides. So square root of 100 is 10. This means side OA equals 10. And side OA is also equal to side OC. So that means side OC equals 10. And side AB equals side CB. So since side AB equals 24, so side CB is also equal to 24. Now, to find the perimeter, we will just add all the sides up. So that's 26 plus 24 plus 10. So that's equal to 60. Example number 4. In our figure, line segment AB is tangent to circle O at point B, and line segment AD is tangent to circle P at point D. Then line segment AC is tangent to circles O and P at point C, and AB equals 24, and the diameter of circle P is 18. Find the perimeter of quadrilateral ACPD. So first, we know that AB equals 24, so that means AC is also 24 and AD is also 24. Since the diameter of circle P is 18, so that means PC, which is equal to PD, equals 9. Now, to find the perimeter of quadrilateral ACPD, we will just add all the sides up. So we have AC plus CP plus PD plus DA. So that's 24 plus 9 plus 9 plus 24, and that is equal to 66. Problem number 5. In our figure, line L is tangent to circle O and circle P at point A and point B respectively. OA equals 18, PB equals 33, and OP equals 39. Find AB. We have two right angles here, and we can draw a line segment from the center of circle O to a point on line segment PB to form a rectangle. And we can name this endpoint here as point C. So OA equals 18, so this means CB also equals 18. And PB equals 33, so this means PC equals 15. And OP equals 39. So we have a right triangle here. So we are going to find OC. Why? Because this OC is equal to AB. Now, since we have a right triangle, we will use Pythagorean theorem. That is C squared equals A squared plus B squared. That's the square of the hypotenuse equals the sum of the squares of the two other sides. So our hypotenuse here is side OP, and we can assign this side PC as A and then side OC as B. So we have side OP squared equals side CP squared plus side OC squared. Substituting, we have 39 squared equals 15 squared plus side OC squared. 39 squared is 1521, and then 15 squared is 225. So that's why we have 1521 equals 225 plus side OC squared. Now subtracting 225 from both sides, so we have 1521 minus 225, that's equal to 1296. So we have 1296 equals side OC squared. Now to get rid of this squared here, we are going to find the square root of both sides. The square root of 1296 is 36. So that means side OC equals 36. Since side OC is equal to side AB, so that means side AB equals 36 units. Thanks for watching, guys. This is Teacher Rejil. Keep safe.